Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Before we start, I'd like to give a huge shout out to our newest tribal elder, Laine. I cannot thank you enough for helping me to keep making these videos. Also, I'd like to thank all my Patreon supporters who are making this series possible through your contributions. Thank you all so much. In this video, we are going to continue optimizing the light-culling shader, where we also touch on various ways of solving the problem with false positives, as well as how to use the wave intrinsics in order to reduce interlocked function calls. A few episodes ago, we started working with compute shaders for constructing the grid frustums and light-culling. I explained how compute shaders are dispatched using multiple thread groups. We can create thread groups that contain up to 1024 threads. For example, currently we are using groups of 256 threads for light-culling. Each thread group has access to a block of memory with a maximum size of 32 kilobytes. We can use this space to define one or more group shared variables that can be accessed by all threads within the group. The local variables are stored in special fast memory, which is called a register file. Each group has a maximum of 64 kilobytes of register space, but this could differ per manufacturer. There is often a maximum of 255 registers that can be used by a thread. However, with 1024 threads in a group, we can only use 64 registers per thread. When we use more registers, the additional memory is allocated on slower non-register memory, which will obviously impact the performance. A GPU consists of many cores that are called compute units by AMD and streaming multiprocessors by NVIDIA. Each of these units can run one or more thread groups concurrently. However, the smallest amount of work can be done on groups of 32 or 64 registers at a time. That means that each line of code operates on that many lanes. This is called a warp by NVIDIA and a waveform by AMD. In HLSL, it's called a wave. Note that a thread group with more than 32 threads will be executed in multiple, possibly concurrent waves. We can try to form a mental model of how the GPU runs this code. Remember, this is only conceptual and in reality it's much more complicated, so please feel free to read as much as you can find on this subject if graphics programming is where you'd like to specialize. Let's pretend that the compiler wouldn't optimize this code. In that case, a load instruction is executed which will load a value of 3 onto 32 or 64 lanes. The second load instruction loads the value of 5. Then a single multiply instruction multiplies the two waves using component-wise multiplication. You can see how this is very similar to SIMD operations on x86 CPUs, where SIMD stands for single instruction, multiple data. Here, a single multiply instruction calculates 32 or 64 values. Now let's say that we continue this code by subtracting x from z, when thread ID's x value is even, and subtract y from z otherwise. In this case, a subtract instruction is executed, which again calculates 32 or 64 subtractions. However, only the lanes for which the branch condition is true will be written to. This is followed by the second subtraction instruction, which again calculates the entire set of values, but only writes to the lanes where the branch condition is true. The resulting vector contains the values that you'd expect. Note how the amount of work that's done by an instruction doesn't depend on the branch. In some cases, where every lane in a wave takes the same branch, the instructions in other branches can be skipped entirely. With HLSL Shader Model 6.0 came the new wave intrinsic functions that make it possible for the threads to gain information about other threads in the same wave. Here you can read all about what these functions are and how you can use them. As we saw earlier, when the wave takes a branch, it will only modify the lanes for which the branch condition is true. These are called active lanes. We can determine if a lane is the first active lane by calling waveIsFirstActive intrinsic function. We can use this in combination with other functions to reduce the number of writes to shared memory. For example, if we wanted to get the maximum value in all active lanes and write it to a group shared variable, we could do it like this. This reduces the number of interlocked function calls by a factor of 32 or 64. In this presentation, you can read about different use cases for wave intrinsics. We are going to use the wave functions to get minimum and maximum depth values and reduce the number of interlocked function calls. We can get the maximum value of all active waves by calling waveActiveMax function. This will compare the depth value of all lanes that took this branch and are therefore active and return the largest value. We can get the minimum value in a similar fashion by calling waveActiveMin. Note, however, that we have to swap the min-max values because we are using reversed depth buffer. And then we use the first active lane to write the min-max values to group shared memory. We still need to use interlocked functions because there are multiple waves per thread group that could be in flight simultaneously. The sampled depth values are transformed to view space and their integer bit representation is written to the group shared variables. Using wave intrinsic functions, we only write to these variables once for a group of 32 or 64 threads. This results in less contention and will speed up this section. However, the performance improvement won't be as large as we have seen so far. As you can see, it works just as before. Looking at our shader, we see that we are not using the light type here anymore. So we can try and remove it from the data in order to make the buffer more compact. Here we can move the type and padding field into the poundif block, where they are only used by the base implementation. This reduces the needed buffer size for the optimized version by a third. We can even rearrange the data in the callable light parameters so that we don't include the type when we are using bounding spheres. This reduces the buffer size by 20%. We'll see later in this video how we render light without having the type explicitly. Starting with the light-culling info, we can encode the light type in cospenumbra variable. Since point lights don't need this field, we can give it a value of -1, for example, to indicate that it's a point light. Now we need to update the C++ code where we fill in cospenumbra and the light type. We can set cospenumbra to -1 when we set the light range. It will contain the actual value if the light is a spotlight. We repeat this for when we add the light-culling info as well. Here we can also only set the light type when the base implementation is used. I think at some point we are going to remove the base implementation, which will make the C++ code simpler. However, I would like to leave it in for now to be used as a reference. Similarly, when we add light parameters, we only set the type when we are not using the optimized shader. Where we don't have direct access to the light type, we can always get it from the lights owner, like this. Now that we are not having the light type in the data, it means that there is also no way for the pixel shader to know which light type it needs to use for rendering. If I comment out this block of code, we can see that we are still able to run the application. We can remove this dependency by sorting the lights by type. So we write the point light indices first, followed by the spotlight indices. For this we need to write a bit of code in the light-culling shader. I'll combine this sorting step with pruning of lights. That means we are going to get rid of false positives that we get as a result of depth discontinuities. As we saw in the previous video, one source of false positives is the method of testing intersections of lights with the grid of frustums. We discussed how we could reduce false positives by using axis-aligned bounding boxes, but ultimately we ended up using our own method of approximate sphere-cone intersection testing. There is, however, another source of false positives, which is caused by the fact that we include lights that intersect the subfrustum even if they don't affect any geometry. We can see this more clearly in this presentation, which is the same as the one we looked at in the last video. Here we can see that because the depth variation is large, or in other words, there is depth discontinuity in this frustum, there is a lot of room for lights to intersect it, even though they don't cover any geometry. There are various ways to improve this situation. One way is what's called 2.5D culling, which slices the subfrustum in a number of partitions in z direction. For example, if we divide the frustum in 32 slices, we could use a 32-bit integer to create a mask for each light and another mask for the geometry in the frustum. Then we can simply bitwise AND these two masks and only include the light if the resulting integer is non-zero. We can have a look at how this is implemented, again in our second favorite engine, which is the Wicket engine. This is the light-culling compute shader again, where we have this function that constructs the bit mask for a light given the depth range of the frustum and the bounding sphere of the light. I think the code is quite self-explanatory, so feel free to pause the video and try to understand how it constructs the bit mask. Next step is to do the same for the geometry in the frustum. This is done by using the sampled depth values and bitwise R-ing the mask for each depth value. Using wave intrinsics, we can update the geometry bit mask with the bit pattern from each wave. The third step is to bitwise AND the two masks in the section where we do the intersection testing. That's pretty much how it's implemented here. There are other ways of tackling this problem, like half C and modified half C, which are also shown in this presentation. Okay, so which one are we going to use, I hear you ask? Well, none of these. And this time, it's partially because I feel a bit lazy, and I also don't think that these methods will be more performant than simply checking if a light affects a pixel. Let me first show you what our solution is, and then I can explain why I think it's probably just as good. We are going to calculate the world space position of each pixel using its screen space coordinate and the sampled depth value, which is in clip space. We use the onProjectUV function with the inverse of view projection matrix to transform from screen space to world space. Then we get the position and direction of each light in this tile from the light-culling info. We can use this information to determine if the pixel is in range of the light, and in case that it's a spotlight, also if the pixel is within the spotlight's cone. we take the dot product of the light vector and the cone direction vector. As you know, the dot product of two unit vectors is equal to the cosine of the angle between the two vectors. If this cosine is larger than cos penumbra, it means that the angle between the two vectors is smaller than the angle of penumbra, and the pixel is therefore within the spotlight's cone. I'm going to add an array of integers with the same length as the maximum number of lights per tile. If a light affects any pixel within the tile, the corresponding element in the light flags array will be set. We must clear the flags before we start. We can use each thread to write zeros into the array. The element's value is 1 for point lights and 2 for spotlights. We can use this later to sort the light indices. Note that we didn't use interlocked functions to write to this array. This is because the elements in this array have values that are constant for all threads. So if a thread calculates a value of 2 for the third element in this array, any other thread that writes to the third element will write the same value. Therefore, race conditions don't cause a problem in this case. This forms the light pruning section, which requires an additional thread synchronization through a call to group memory barrier function. As you can see, the computational cost here is not as high as the other methods, especially if we keep in mind that most tiles in a real-world game don't even have any lights, and the ones that do typically have a small number of lights. In addition, because the flags here have a value depending on the light type, we can use them to sort our lights by type, thus getting rid of the branching in the pixel shader, as we'll see later in this video. That said, I do recommend to try other implementations for practicing and learning. Now we are going to update the light grid with the number of remaining lights. First, we need to count the number of point lights and spotlights. We do this by counting the flags for each type. We can get the light index start offset as we did before. However, because we are going to write the indices for spotlights after the point lights, we need an additional start index for spotlight indices. This is another group shared variable that I'm going to add in a minute. It's simply the light index start offset plus the number of point lights. This is where we start writing the spotlight indices. Now, instead of using the total number of lights, we put the number of point lights in the upper half and the number of spotlights in the lower half of the light count integer in the light grid. I'll add the index start offset variable for spotlights next. We don't have to initialize this one because we set its value once right here. The last section of the shader is where we write the light indices into the light index buffer. Here we want to write the point light indices first, followed by spotlight indices. So first of all, we need to check the value of each light flag. Then we write point light and spotlight indices to the buffer. However, because we are using all threads in the thread group, we need to keep two additional offset variables, which must be group shared. These are like pointers that are advanced after an index for each light type has been written into the buffer. Let me sort out the braces here. By the way, note the subtle use of light count here. Remember, the number of lights that actually affect this tile could be smaller, but we need to check the flags for the initial number of lights before pruning. We are also doing some things here that are not good for performance, things like branching and interlocked function calls. However, remember that the number of lights per tile is low for real-world scenarios, so this probably looks worse than it actually is. Anyway, here we get the next index within the buffer, where we can write the light index for the point light. And we repeat this for spotlights. This is all for the light-culling shader. Let me run the application and fix my typos. Here's one that's missing a semicolon. Spotlight is with lowercase l. And I have no idea what this is. I see I forgot to initialize the group shared index variables that we just added. They should be initialized to 0 before use. Great, it runs. We need to read the light information in the pixel shader next. If you're not using the optimized shader, we can run the old shader code. Otherwise, we need to read light indices in the new order. Here we get the number of point lights and spotlights. Then instead of a loop with branching for light type, we have two loops for point lights and spotlights. Ha, that looks magical, doesn't it? Probably made a small typo somewhere. Oh, I see, here is a copy-paste error. Forgot to use the index offset for spotlights. Nice, we got it working again. Let's see if our latest optimization made any difference. We get 49 FPS for 64,000 lights. And 387 FPS for 4,000 lights. So we got faster for scenes with large number of lights and a bit slower when we have fewer lights. Again, this might prove to be more efficient when the pixel shader is more complicated than it is now. Remember, we did the last optimization to spare the pixel shader from doing unnecessary work. Therefore, I'm going to leave it like this, and if later on it keeps being slower, then we can revert back to how it was. However, I'm pretty sure that won't be the case, but who knows, even I could be wrong sometimes, eh? Anyway, we are still 2.5 times as fast as when we started, so I'd say it's been good progress. This was supposed to be the last part of this episode. However, we still have a trick up our sleeves, which I'd like to show you in the next video. So make sure that you tune in if you find this kind of thing interesting. As always, thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!